Hello friends, I hope you all are fine and taking care of yourself. So continuing with the topic reciprocating air compressors, in the last lectures we had discussed the classification working of reciprocating air compressors, then the expression for work done, then multi-stage compression has also been discussed with you. In this lecture, I'll be discussing another important term associated with this reciprocating air compressors. It is isothermal efficiency. So we'll be discussing the term isothermal efficiency specifically in this lecture. So in the previous lecture, we had studied how to draw this PV diagram and how this PV diagram shows or represents different processes of the reciprocating air compressor. In that PV diagram in the last lecture we had discussed that the compression process is primarily considered to be polytropic. However, this compression process can also be considered to be an adiabatic process or the isothermal process as well, along with this polytropic process. It means that this compression process can have these three variants. You can say either the process is considered to be isothermal. This 1 to 2 double dash is this is isothermal process. 1 to 2 dash, it is polytropic process, and 1 to 2 is this adiabatic. So this is the graph without clearance, and this is the PV diagram of the compression cycle with clearance, right? And this is the TS diagram, temperature entropy chart, which represents these three compression processes on the TS diagram. So 1 to 2 it is adiabatic, so it is a reversible isentropic process, so it will be a vertical line. 1 to 2 double dash, it is isothermal process, so it will be a horizontal line on this TS plot. And 1 to 2 dash is a polytropic process, so it will be having a curve. Now in this PV diagram we can see that the minimum area is being covered by the process considered to be 1 to 2 double dash, that is the isothermal process. So this PV diagram will be having minimum area if the process is considered to be an isothermal, and the maximum area is when the process is considered to be the adiabatic process, right? Polytropic will be lying somewhere in between the isothermal and the adiabatic process, right? So now, this has been discussed in this part, so that the compression of air in the compressor may be carried out following number of thermodynamic processes, such as isothermal compression, it may be polytropic compression, or it may be the adiabatic compression. We have seen that the work requirement is maximum with the adiabatic process, as I shown you in the previous slide, that the work requirement will be maximum with the adiabatic process, right? And it is minimum with the isothermal process, right? So as a designer, one shall be interested in a compressor having minimum compression work requirement, and ideally compression should occur isothermally for minimum work input. In practice, it is not possible to have isothermal compression. Why so? Because for an isothermal process to occur, the conditions are that the process should occur very slowly, and the heat rejected out of that system should maintain that same temperature within the system, right? But actually, due to high running speed of compressor, the compression process may be assumed to be nearly adiabatic or the polytropic process, following this law PV raised to power n is equal to C, with value of n varying between 1.25 and 1.35 for air, right? Ideally the compression process should be isothermal, but actually because of high speed this process is not practically possible. Isothermal compression is practically not possible because of the high speed. So the process is considered to be nearly adiabatic or the polytropic process, as we discussed earlier. So it is obvious that the compression process should be compared with the isothermal compression process. Actual compression process, that is either adiabatic or the polytropic process, it should be compared with the isothermal compression process, and the mathematical parameter called isothermal efficiency is defined for quantifying the degree of deviation of actual compression process from the ideal compression process. That is, we have to compare uh, the work requirement for the compression, considering the process to be either polytropic, or we'll be comparing it with the isothermal compression, because isothermal compression will be requiring minimum work input. So we'll be comparing the actual process with the ideal process, that is the isothermal. Actual process is either adiabatic or the polytropic, right? So this isothermal efficiency, the term, it has been defined as the ratio of isothermal work by actual indicated work, right? Isothermal work would be less than the actual indicated work, so this factor would be less than 1. So in the last lecture we had seen that the work done by compressor, considering the process to be polytropic, these two expressions were derived last time. That is, work done for compressor is n by n minus 1 mr T2 minus T1 for this polytropic process, and similarly it can also be written as n by n minus 1 mr T1 P2 by P1 n minus 1 by n minus 1. So these two expressions were derived last time for the work done for a compressor. And if the process is considered to be adiabatic, this will be the expression, that is, now the n will be replaced with gamma, that is the adiabatic index. So it will be gamma by gamma minus 1 mr T2 minus T1, right? Or the adiabatic work done can also be determined by this expression mCp T2 minus T1, that is the specific heat at constant pressure, or it can be written as m into H2 minus H1, the change in enthalpy. As we know that in adiabatic process, no heat is added or rejected to the system, so the work done will be equal to the change in enthalpy of the system, right? Now if the work done is considered, if the process is considered to be isothermal, then the expression for work done will be P1 V1 natural log of the R, where R is the ratio of V1 by V2. We know that the expression for work done for isothermal, it is P1 V1 log V1 by V2. So this will be the expression for work done considering the process to be isothermal. Now the isothermal efficiency will be P1 V1, that is the work done by isothermal considering the process to be isothermal. So P1 V1 log natural R, where R is V1 by V2, divided by n by n minus 1 P1 V1 P2 by P1 n minus 1 by n minus 1. So this will be the expression for isothermal efficiency, that is the work done by the isothermal process over the work done by considering it to be the polytropic process. And similarly it can also be replaced with the adiabatic process if the process is considered to be actually the adiabatic. Now the isothermal efficiency of the compressor should be close to 100%, because which means that the actual compression should occur following a process close to isothermal process. So the actual compression process should be near to the isothermal process, so this factor will be close to 100%. So as a designer, every designer wants that the work requirements for the compression should be minimum, so this should be close to the 100%. For thus the mechanism be derived to maintain a constant temperature during the compression process, and a number of arrangements can be used for faster heat dissipation. So the first arrangement that can be used is that is a faster heat dissipation from inside of compressor to outside by use of fins over the cylinder. In the last lecture we had seen the construction of uh, the reciprocating compressor, and we had seen that there were some cooling jackets, and there may also be some fins extended beyond the surface, which will increase the surface area of this outer cylinder, and it will increase the cooling rate, so that will be faster heat dissipation, right? And next point is water jackets may be provided. As I shown you in the diagram, water jackets were provided so that the heat can be picked up by the cooling water circulating through the water jacket. In another arrangement, the water may also be injected at the end of compression process in order to cool the air being compressed. However, this arrangement is not popularly used. In another case, as we have seen in the multi-stage compression, an intercooler was used. So in case of multi-stage compression and different compressors operating serially, the air leaving one compressor may be cooled up to the ambient state. This cooling of fluid being compressed between the two consecutive compressors is called intercooling and is frequently used in case of multi-stage compressors. So to in order to have the minimum work requirement, this intercooling is done in case of multi-stage compression in order to have maximum isothermal efficiency, right? So the next lecture will be discussing some more articles based on this topic.